Look up at the night sky, and you'll see countless stars shining with steady, predictable light, each one a distant sun, following the familiar rhythms of the cosmos. But what if I told you there's a star out there that doesn't play by the rules? A star that dims and flickers in ways so strange, so utterly baffling, that even the brightest minds in astronomy are left scratching their heads. Meet KIC 8462852, better known as Tabby's star, a cosmic mystery that has sparked wild theories, heated debates, and one terrifying question: could this be something more than just a star? Something artificial, discovered in data from NASA's Kepler Space Telescope. Tabby's star behaves like no other. Most stars dim slightly when planets pass in front of them, a predictable, rhythmic dip in brightness. But this star, its light doesn't just dip, it plunges. Erratic, dramatic drops of up to 20%, sometimes lasting for days, with no clear pattern or explanation. No known natural phenomenon, not planets, not dust clouds, not even swarms of comets, can fully account for what's happening here. The numbers don't add up. The behavior defies logic, and that's where things get really interesting. Because when science runs out of answers, imagination takes over. Could these strange dimming patterns be the fingerprints of an advanced civilization? A megastructure built by an alien species to harness the star's energy. It sounds like science fiction, but for a while, it was a legitimate scientific hypothesis. And even now, after years of study, Tabby's star keeps its secrets close. Every new observation deepens the mystery, pulling us further into a cosmic detective story with no easy answers. So buckle up, because today, we're diving into one of the universe's most tantalizing enigmas, a puzzle that challenges everything we think we know about the cosmos and our place within it. The story of Tabby's star begins not in a high-tech observatory, but in the homes of everyday people, citizen scientists scanning data from NASA's Kepler Space Telescope. Launched in 2009, Kepler was designed to hunt for exoplanets by detecting the tiny, regular dips in a star's brightness caused by orbiting worlds. For years, it monitored over 150,000 stars, collecting mountains of data, but in 2015, something strange surfaced. Buried in the numbers was a star unlike any other. KIC 8462852. What made it stand out? Most planet-caused dimming events are subtle, predictable, lasting just hours. But this star's light didn't fade gently. It plummeted in bizarre, irregular bursts. Some dips lasted days, with drops so severe they defied explanation. Imagine a flickering light bulb, but on a cosmic scale, a star that dimmed by up to 20% for no apparent reason. Astronomers were stunned. Natural phenomena like planets or dust clouds couldn't account for such extreme, erratic behavior. Here's where the plot thickens. The initial discovery wasn't made by professional astronomers. It was volunteers from the Planet Hunters Project, ordinary people sifting through Kepler's data, who first flagged the anomaly. Armed with nothing but curiosity and a computer, these citizen scientists spotted what automated algorithms had missed. Their findings sent shockwaves through the astronomy community, sparking a race to understand what could possibly cause such wild fluctuations. Was it a cosmic collision, a swarm of comets, or something even more extraordinary? The mystery had just begun, and the answers, if they existed, were hiding in the star's unpredictable dance of light. To understand just how bizarre Tabby's star truly is, let's first look at how normal stars behave. When a planet orbits its sun, it occasionally passes between the star and our telescopes, a phenomenon called a transit. These transits cause tiny, predictable dips in brightness, usually less than 1%, and they occur like clockwork. Picture a moth fluttering past a porch light, the dimming is slight, regular, and over in minutes. That's how exoplanet hunting works. Now, imagine that same porch light suddenly plunging into near darkness for days at a time, flickering erratically, with no discernible pattern. That's Tabby's star. Its dimming events aren't just unusual, they're downright extreme. Some drops reach a staggering 22%, like someone intermittently throwing a cosmic curtain over the star. For comparison, if Jupiter, our solar system's largest planet, transited the Sun, it would block just 1% of the light. Tabby's star's behavior suggests something far more massive, more irregular, and utterly unlike anything we've seen before. Initial theories pointed to swarms of comets, and perhaps a family of them breaking apart and creating vast clouds of debris. But calculations quickly revealed a problem. You'd need an implausible number of comets, more than our solar system has ever produced, to explain the star's deepest dimming. Dust clouds, they'd scatter light differently than what we observe. Even a rogue planet tearing apart wouldn't account for the star's long, irregular dips. Then came the real curveball. The data showed the star's overall brightness has been fading over the past century. Historical archives revealed Tabby's star dimmed by about 14% between 1890 and 1989. Combined with its erratic modern behavior, this long-term trend makes the mystery even harder to crack. Natural explanations strain under the weight of the evidence, leaving scientists chasing shadows in the data. What could possibly cause such dramatic, unpredictable changes? The answer, or lack thereof, has turned this unassuming star into one of astronomy's greatest puzzles. When astronomers first grappled with the mystery of Tabby's star's erratic dimming, one early hypothesis emerged as a leading contender: a colossal swarm of comets. Picture this: a family of icy bodies, hundreds of thousands strong, circling the star in a chaotic orbit. As they pass close to its heat, they fracture, releasing vast plumes of dust and gas. These clouds could, in theory, block starlight intermittently, creating the irregular dips we observe. It was an elegant solution, rooted in known cosmic phenomena. After all, our own solar system has the Oort cloud, a distant repository of icy objects that occasionally sends comets spiraling inward. Scale that up, and maybe, just maybe, you'd get the bizarre light patterns of Tabby's star. The comet swarm theory gained traction because it checked some critical boxes. Dust from disintegrating comets scatters light in ways that align with certain aspects of Tabby's star's dimming patterns. Plus, the idea didn't require inventing entirely new physics. It was a cosmic Occam's razor, the simplest explanation, using mechanisms we've seen elsewhere. Researchers even calculated that a truly massive comet family, far larger than anything in our solar system, might explain the deepest observed dips. For a time, it seemed like the puzzle had a plausible answer. But skepticism grew as scientists crunched the numbers. To match the star's most extreme dimming events, you'd need an implausible number of comets, not just hundreds of thousands, but millions, all breaking apart in perfect synchrony over centuries. The energy required to shatter and vaporize so many icy bodies would be staggering, and the resulting debris should have left other detectable signatures, like excess infrared heat from warmed dust. Yet observations from instruments like the Kepler Space Telescope found no such excess. Worse, the star's long-term dimming over a century added another wrinkle. Comets might explain short-term dips, but they couldn't account for a steady, decades-long fade. The final blow came when astronomers realized the dimming wasn't just deep, it was achingly inconsistent. Comet swarms, even chaotic ones, should produce some semblance of periodicity, a rough rhythm to the shadows they cast. But Tabby's star's light curves looked more like a random scribble than a repeating pattern. The data refused to fit the mold, leaving researchers with a troubling realization. If comets weren't the answer, what was? The door swung wide open for wilder ideas, including one that set the astronomy world ablaze: the possibility that we were witnessing something not natural, but engineered. The comet theory had been a safe harbor, but now the waters of mystery grew deeper and darker than ever. Out of the frustration with natural explanations came one of the most audacious ideas in modern astronomy. What if we're not looking at a natural phenomenon at all? In 2015, Penn State astronomer Jason Wright dropped a bombshell. The bizarre dimming of Tabby's star might not be caused by comets or dust, but by something far more extraordinary: an alien megastructure. Specifically, he proposed the star could be partially encircled by a Dyson swarm, a hypothetical construct theorized by physicist Freeman Dyson in the 1960s. The concept was simple yet staggering. An advanced civilization might build massive solar collectors around their star to harness its energy, creating irregular shadows as these structures orbit. Wright's hypothesis wasn't pulled from thin air. The numbers lined up eerily well. A Dyson swarm, whether made of giant panels, orbiting habitats, or other energy-capturing technology, would block starlight in unpredictable, asymmetrical patterns, just like Tabby's star's dips. Unlike natural debris, these megastructures wouldn't emit excess infrared radiation, which explained why telescopes hadn't detected the heat signature expected from dust clouds. Even the century-long dimming fit, an alien civilization might slowly expand its swarm over generations, gradually blocking more light. Suddenly, the most outlandish explanation became the one that answered the most questions. The media pounced, dubbing it the alien megastructure star, and public imagination went into overdrive. Tabby's star became a cultural phenomenon, blending science with science fiction in a way few discoveries ever had. But within the scientific community, reactions were mixed. Some researchers welcomed the bold thinking. After all, science thrives on testing even the wildest ideas. Others bristled at the headlines, arguing that invoking aliens should always be a last resort. Yet no one could deny the strangeness of the data. As astronomer Tabby, the star's namesake, put it, "We don't know what's happening here, and that's what makes it exciting." Critics pointed out the glaring hole in the theory. Extraordinary claims require extraordinary evidence, and there wasn't any direct proof of aliens. Alternative explanations, like uneven dust distributions or interstellar material, still had legs. Plus, nature has a history of serving up bizarre phenomena that later find mundane explanations. Think pulsars, initially mistaken for extraterrestrial signals. Still, the megastructure hypothesis did something crucial. It pushed scientists to think bigger. If they couldn't prove aliens, they could at least rule out every other possibility. And so far, that's proven harder than anyone expected. Tabby's star refuses to fit neatly into any box, leaving the door cracked just enough for wonder. Whether it's aliens or some yet undiscovered cosmic quirk, one thing's clear: this star has rewritten the rules, and we're still scrambling to catch up. The moment the alien megastructure hypothesis hit the scientific stage, it was met with a mix of fascination and fierce skepticism. While the idea captured the public's imagination, many astronomers raised an immediate red flag, invoking Carl Sagan's famous adage, "Extraordinary claims require extraordinary evidence." And the truth was, no such evidence existed, just a tantalizing, unexplained pattern of dimming. The scientific method demands rigor, and without concrete proof, the burden was on proponents to rule out every possible natural explanation before leaping to interstellar engineering. Critics pointed to history as their guide. Time and again, cosmic mysteries initially attributed to aliens had turned out to be bizarre but entirely natural phenomena. Take pulsars, for instance. Their perfectly timed radio signals were once thought to be beacons from an advanced civilization, until astronomers discovered they were the work of rapidly spinning neutron stars. Even the famous WOW signal, a strong narrowband radio burst detected in 1977, remains unexplained but is widely assumed to have a natural origin. The lesson: the universe is full of surprises, and jumping to aliens is often a shortcut to being wrong. Alternative theories began to emerge, each attempting to explain Tabby's star's odd behavior without invoking extraterrestrial builders. One leading idea proposed an uneven ring of dust, not the uniform clouds seen around young stars, but a lopsided debris field, perhaps the remnants of a catastrophic planetary collision. This could create irregular shadows as clumps of material orbited the star, blocking light unpredictably. Another suggestion was interstellar medium interference, floating patches of gas and dust between the star and Earth, acting like cosmic frosted glass. Then came the Trojan asteroid hypothesis. Imagine two massive asteroid swarms, locked in gravitational resonance, ahead of and behind a planet's orbit, casting staggered shadows as they moved. Computer simulations showed such a configuration might produce erratic dimming, though the scale required stretched the limits of plausibility. Other researchers floated the idea of a massive, disintegrating exomoon, a moon torn apart by tidal forces, its debris spiraling into the star in fits and starts. The most compelling natural explanation, though, involved the star itself. Some astronomers speculated that Tabby's star might be undergoing rare internal convulsions, a phase of stellar instability that caused sporadic eruptions or magnetic storms, temporarily darkening its surface. Young stars are known to behave erratically, but Tabby's star wasn't young. Unless it was a very peculiar outlier, this theory, too, fell short. What united all these counterarguments was a simple principle: science moves cautiously. The burden of proof wasn't on skeptics to disprove aliens. It was on proponents to eliminate every mundane possibility first. And as observations continued, even the staunchest supporters of the megastructure hypothesis admitted the evidence just wasn't there. No repeating patterns, no radio signals, no technosignatures, just that infuriating, beautiful mystery. Yet in a way, the backlash was as valuable as the original hypothesis. It forced astronomers to think creatively, to test the limits of known physics, and to collaborate across disciplines in ways they hadn't before. The debate wasn't about shutting down curiosity, it was about channeling it productively. Because sometimes the most exciting answer isn't aliens, but we don't know yet, and that uncertainty is where discovery begins. As the mystery of Tabby's star gripped the scientific community, astronomers worldwide turned their telescopes toward this enigmatic flicker in the constellation Cygnus. The Kepler Space Telescope had provided the initial data, but its mission was winding down, so researchers mobilized other instruments to keep watch. The Hubble Space Telescope, with its razor-sharp vision, aimed its cameras at the star, hoping to catch ultraviolet clues hidden in its light. Meanwhile, The Spitzer Space Telescope, sensitive to infrared wavelengths, scanned for the heat signatures of dust or debris. Ground-based observatories joined the hunt too, their massive mirrors tracking every fluctuation in real time. The goal was simple: catch the star in the act of dimming and maybe, just maybe, decode its secrets. What they found only deepened the intrigue. Hubble's observations revealed something startling: the star's dimming wasn't uniform across all wavelengths. When Tabby's star faded, its blue light dimmed more sharply than its red light. This wasn't what you'd expect from a solid object, like a planet or megastructure, blocking its light. Instead, it pointed toward something diffuse and fine-grained, like dust particles, scattering shorter wavelengths more effectively. Spitzer's infrared eyes, however, delivered a curveball. There was no excess heat from warm dust, which should have been present if vast dust clouds were the culprits. The data contradicted itself, leaving scientists staring at two pieces of a puzzle that refused to fit together. Ground-based telescopes added another layer of complexity. During one of the star's dramatic dimming episodes in 2017, the Los Cumbres Observatory Network captured real-time data showing the light drop was uneven, almost patchy. Some wavelengths dimmed faster than others, as if whatever was blocking the star wasn't just a single object, but a shifting, asymmetrical swarm. Then, in 2019, the star did something entirely new. It flickered rapidly over just a few days, like a candle guttering in the wind. These micro-dips, caught by the Keck Observatory in Hawaii, defied all predictions. Even more perplexing was the long-term trend. Careful analysis of century-old photographic plates from Harvard's archives showed Tabby's star had gradually faded by roughly 14% between the late 1800s and the 1980s. But modern observations revealed the dimming wasn't steady. It accelerated sporadically, with no clear cause. Theories abounded. Maybe the star was ingesting a planet, causing temporary darkening. Perhaps it was surrounded by a massive, warped debris disk tilted at a strange angle. Or maybe, just maybe, there was no single explanation, but a combination of weird astrophysics we hadn't yet uncovered. What became clear was this: every new observation chipped away at simple explanations without offering a definitive answer. The more data we gathered, the less Tabby's star made sense. It wasn't just resisting categorization, it was actively taunting us, serving up contradictions with every fresh round of observations. And that's the heart of scientific discovery, not the answers we expect, but the questions we never saw coming. Tabby's star, in all its stubborn strangeness, had become more than a curiosity. It was a mirror, reflecting back just how much we still have to learn about the universe. One of the most promising breakthroughs in solving the Tabby star puzzle came when scientists took a closer look at an old cosmic culprit: dust. Not the uniform, predictable dust we imagine, but something far trickier: microscopic particles scattered unevenly across space, acting like a celestial veil that filters starlight in strange ways. Detailed observations revealed the star's dimming wasn't random chaos, it followed a telltale pattern. When light passed through this dust, shorter blue wavelengths scattered more dramatically than longer red ones, explaining why the star's brightness dropped unevenly across different colors. It was a subtle clue, but for researchers, it was like finding a fingerprint at a crime scene. The dust hypothesis gained traction because it neatly explained several perplexing observations. Think of it like sunlight filtering through a smoky sky. The thicker or more clumped the smoke, the more uneven the dimming. In Tabby's star's case, the dust isn't in a tidy ring or cloud, but likely drifting in transient, asymmetrical clumps. Some studies suggested it could be debris from colliding asteroids or evaporating comets, creating a patchy, ever-shifting screen around the star. This would account for the erratic dips. No two dimming events would look exactly the same because the dust's distribution changes over time. But there's a twist. Ordinary interstellar dust should produce excess infrared radiation as it absorbs and re-emits starlight as heat. Yet Tabby's star showed no such infrared excess, leaving scientists puzzled. How could dust block visible light without glowing in the infrared? The answer might lie in the dust's composition. Recent research proposes the particles could be unusually large, more like fine gravel than typical space dust, or made of exotic materials that don't heat up the same way. Alternatively, the dust might be positioned just right, far enough from the star to stay cold but close enough to cast a shadow when viewed from Earth. Perhaps the most compelling evidence for dust came in 2018, when Tabby's star underwent another dramatic dimming episode. This time, astronomers were ready. Using the Las Cumbres Observatory network, they captured high-precision measurements across multiple wavelengths. The data showed a clear wavelength-dependent dimming pattern, exactly what you'd expect from light scattering off dust grains. Even the star's long-term fading over the past century could fit this model if the dust cloud is slowly expanding or accumulating. Yet the mystery isn't entirely solved. Dust explains much of the star's odd behavior, but questions linger. What's creating this dust in such vast, irregular quantities? Could it be the aftermath of a cataclysmic planetary collision, or the slow disintegration of a massive comet swarm? And why does the dust seem to cluster in ways we've never seen around other stars? Each answer peels back another layer, revealing just how complex and dynamic planetary systems can be. Tabby's star may not harbor alien megastructures, but it's teaching us something equally valuable, that the universe still holds surprises hiding in plain sight, waiting for us to look closer. While the erratic dimming episodes of Tabby's star captured headlines, an even more perplexing discovery lurked in the archives, one that rewrote the timeline of this cosmic mystery. When astronomers combed through historical observations, they found something startling. This star wasn't just flickering unpredictably in the present day. It had been quietly fading for over a century, like a light bulb slowly burning out. Old photographic plates from Harvard's astronomical archives, dating back to the late 1800s, revealed the star had dimmed by roughly 14% between 1890 and 1989. This wasn't a temporary blip, it was a relentless, decades-long decline, adding a chilling new dimension to the puzzle. What makes this long-term trend so baffling is the sheer scale of time involved. Stars like our Sun are remarkably stable over centuries, their brightness varying by less than 1% across human lifetimes. For Tabby's star to fade so dramatically defies everything we know about stellar behavior. Imagine watching a campfire dwindle not because the flames are dying, but because something invisible is steadily piling more logs onto the fire, blocking its glow. That's the level of strangeness we're dealing with here. One theory suggests the star might be cloaked in a vast, uneven shroud of cosmic dust, not just the patchy clouds causing short-term dips, but a sprawling reservoir of particles drifting gradually into place. Picture fog rolling in over decades, thickening just enough each year to obscure a little more light. But there's a catch. Most dust clouds around stars are either static or dissipating over time. For dust to accumulate so persistently would require a continuous source, perhaps a disintegrating planet or a relentless bombardment of comets. Both scenarios with no known parallels in astronomy. Another possibility hinges on the star itself. Some researchers speculate Tabby's star could be recovering from a cataclysmic event, a collision with another massive object, or an internal upheaval that ejected enormous amounts of debris. The fading light might then be the aftermath, like stellar bruises slowly healing. Yet spectroscopic analysis shows no signs of such trauma in the star's composition, leaving this idea on shaky ground. Even more radical explanations have been floated, from interstellar gas clouds passing between us and the star to hypothetical dark matter clumps interacting in ways we don't yet understand. The most unsettling aspect of this century-long dimming, it's still happening. Modern observations confirm the trend isn't just historical. Tabby's star continues to lose brightness today, though not at a steady rate. Some years it fades faster, others it holds steady, as if whatever's obscuring it has a mind of its own. This rules out simple explanations like instrument error or calibration issues across different telescopes. The data is real, the trend is undeniable, and the implications are profound. We're witnessing a cosmic process unlike anything in our astrophysical playbook. What began as a curiosity about erratic dips has morphed into a far deeper mystery, one that spans generations of human observation. Tabby's star isn't just behaving oddly in the present, it's been quietly defying expectations for longer than any living astronomer has been alive. And that raises a humbling question. If even the slow, patient changes of the cosmos can confound us so completely, what else might we be missing in the vast, whispering dark? The idea of a massive planetary collision around Tabby's star isn't just science fiction. It's a real possibility astronomers have seriously considered. Picture this: two worlds, each potentially larger than Jupiter, slamming into one another with unimaginable force. The resulting debris field would be catastrophic, scattering trillions of rocky fragments into orbit. Over time, these shattered remains could form an irregular cloud, blocking starlight in erratic bursts as they drift between the star and Earth. It's a compelling explanation, especially when you consider the star's deep, irregular dimming patterns. After all, cosmic smash-ups aren't unheard of. Our own solar system likely witnessed similar chaos during its violent early history. But does the math hold up? For a collision to explain Tabby's star's behavior, the debris would need to linger for centuries, continuously obscuring the star's light. That's a problem. Most planetary collisions, even colossal ones, tend to clear relatively quickly, with debris either falling into the star or dispersing into space. Plus, the energy released in such an event should have left behind telltale signs, like a temporary brightening from heated debris or infrared emissions from warm dust. Yet observations show no evidence of this aftermath. Even more puzzling, the star's century-long dimming trend suggests something more sustained than a one-time cataclysm. If a collision happened, it would have needed to occur far enough in the past for the initial fireball to fade, but recent enough for the debris to remain dense, a cosmic Goldilocks scenario that strains credulity. Another intriguing natural theory involves the destruction of an exomoon, a moon ripped apart by tidal forces as it spiraled too close to its host planet. Imagine a world like Jupiter's moon Io, but on a far grander scale. As the moon disintegrates, its shattered fragments could create a sprawling ring of debris, casting irregular shadows as they orbit. This might explain why the dimming events lack a clear pattern. The remnants wouldn't be uniformly distributed, leading to patchy, unpredictable eclipses. Some researchers have even suggested that tidal disruption could release plumes of dust periodically, matching the star's observed flickering. Yet this hypothesis, too, faces hurdles. For a moon's destruction to produce enough debris to obscure a star as dramatically as Tabby's star, the moon would need to be impossibly massive, far larger than any moon we've discovered. Even then, the resulting debris should emit detectable infrared radiation as it absorbs starlight, but no such signal has been found, and just like the planetary collision theory, the timing doesn't quite fit. The process of tidal disruption is relatively quick on cosmic scales, lasting perhaps thousands of years, not the century-spanning fade we've documented. Then there's the dust cloud theory, currently the most favored explanation, but not without its own wrinkles. Unlike uniform rings around young stars, Tabby's star's dust appears clumpy and uneven, drifting in ways that defy simple models. Some researchers propose it could be interstellar dust, floating between the star and Earth rather than orbiting the star itself. This would explain the lack of infrared excess, since cold, distant dust wouldn't heat up enough to glow. But interstellar dust usually affects multiple stars in a region, not just one. Why would Tabby's star be singled out? Other scientists point to dynamic dust particles trapped in complex orbital resonances with unseen planets, creating ever-shifting shadows. It's a clever solution, but it requires a precise and fragile arrangement of gravitational forces to sustain the observed dimming patterns over time. Nature rarely keeps such perfect chaos in balance. What ties these theories together is their shared challenge. Each one explains part of the mystery, but stumbles over another. A planetary collision accounts for erratic dimming, but not the long-term fade. A disintegrating exomoon fits some light curves, but demands unrealistic scales. Dust clouds answer wavelength-dependent dimming, but struggle with the missing infrared signature. It's as if Tabby's star is a cosmic jigsaw puzzle where none of the pieces quite fit. And that's precisely what makes it so fascinating, because every dead end forces us to rethink what's possible. Whether the answer lies in an overlooked natural process or something entirely new, one thing's certain: this star isn't done surprising us yet. At the heart of the Tabby's star mystery lies a fundamental question: could the star itself be the culprit? After all, stars aren't static beacons, they're dynamic, roiling spheres of plasma, capable of wild outbursts and subtle quirks. Some stars, like Cepheids variables, pulse rhythmically, brightening and dimming over days or weeks. Others, like flare stars, unleash violent eruptions of magnetic energy. Could Tabby's star simply be going through an unusual phase of stellar adolescence or turmoil? Stellar physics offers a few possibilities, but each one comes with its own set of contradictions. Take magnetic activity, for instance. Our own sun experiences sunspots, cooler, darker patches caused by intense magnetic fields that can slightly reduce its brightness. In extreme cases, stars with hyperactive magnetic fields exhibit starspots so massive they cover entire hemispheres, causing significant dimming. But here's the catch: Tabby's star's light dips aren't periodic like starspot rotations. They're erratic, asymmetrical, and far too dramatic. Even the most magnetically active stars don't drop in brightness by 20% overnight. Plus, Tabby's star is an F-type main sequence star, a category not known for extreme magnetic behavior. Spectroscopic analysis reveals no unusual activity in its atmosphere, no telltale signatures of the violent flares or spots that might explain its antics. Then there's the idea of pulsations. Some stars, like our Lyrae variables, expand and contract regularly, their brightness waxing and waning as their outer layers heat and cool. But these pulsations follow precise rhythms, like a cosmic metronome. Tabby's star's dimming is anything but rhythmic. It's a chaotic symphony with no discernible tempo. Even stranger, pulsating stars typically change brightness across all wavelengths simultaneously. Tabby's star, by contrast, dims more in blue light than red, a fingerprint that points to something blocking its light rather than an internal process. Another stellar quirk to consider is mass loss. Aging stars sometimes shed their outer layers, creating shrouds of gas and dust that obscure their light. But Tabby's star isn't old or massive enough to be in this phase. It's a middle-aged star, squarely in the prime of its life, with no spectral evidence of the heavy elements or ionized gases you'd expect from such an eruption. Even if it were shedding material, the process would be gradual, not the abrupt, jagged dips we observe. Perhaps the most exotic stellar explanation involves a recent collision or merger. If Tabby's star had engulfed a smaller companion or absorbed a rogue planet, the resulting turbulence could throw it into temporary chaos. Mergers can trigger outbursts, dust production, and irregular dimming. But mergers are messy affairs. They leave behind glowing debris and chemical anomalies in the star's spectrum. Tabby's star shows no such signs. Its composition is normal, its atmosphere unremarkable. There's no infrared glow from warm debris, no lithium or other tracers of a recent cataclysm. What's striking is how thoroughly Tabby's star defies every known category of stellar misbehavior. It's not a variable star, not a flare star, not a merger remnant. It's something else entirely, a cosmic outlier that refuses to fit the mold. And that's what makes this mystery so compelling. Every time we think we've pinned down an explanation, the star throws another curveball, forcing us to question whether we're missing a piece of stellar physics altogether. Maybe the answer isn't in the textbooks yet. Maybe Tabby's star is writing a new chapter, one we're only beginning to decipher. When Tabby's star burst onto the scene, it didn't just captivate astronomers, it ignited a media firestorm. Headlines screamed about alien megastructures, documentaries raced to dramatize the mystery, and sci-fi authors seized the star as a jumping-off point for tales of cosmic civilizations. Suddenly, a faint point of light 1,500 light-years away was trending on social media, its name shorthand for humanity's deepest existential question: are we alone? The frenzy wasn't just about science, it was about storytelling, speculation, and the irresistible allure of the unknown. The turning point came when Penn State astronomer Jason Wright floated the Dyson swarm hypothesis. Overnight, Tabby's star became a Rorschach test for the public imagination. For some, it was proof that science could still dream big. For others, a cautionary tale about jumping to extraterrestrial conclusions. News outlets, hungry for clicks, amplified the alien angle with breathless coverage. "Have we found evidence of advanced alien life?" blared one headline. "Scientists baffled by star that could harbor alien tech," declared another. Even reputable science programs framed the star as a potential first contact scenario, blurring the line between hypothesis and hype. Documentaries piled on, splicing ominous music with artist renditions of Dyson swarms, glittering rings of solar panels encircling the star. One production staged a dramatic reenactment of astronomers gasping at light curve data, as if they'd glimpsed a UFO. Sci-fi writers, meanwhile, spun the mystery into novels and screenplays. A popular TV series even featured a fictionalized version of Tabby's star, complete with shadowy alien architects and interstellar conspiracies. The star wasn't just an object of study anymore, it was a cultural icon, a blank canvas for humanity's hopes and fears about the cosmos, but beneath the spectacle, a tension simmered. Many scientists cringed at the oversimplifications, worrying the hype would eclipse real research. Astronomer Tabby, the star's namesake, found herself in an awkward position. Her team's careful work was now mired in extraterrestrial speculation. At conferences, she'd patiently explain that aliens was always a last resort hypothesis, but the nuance rarely made headlines. Meanwhile, skeptics pushed back hard. Astrophysicist Ethan Siegel famously called the media coverage irresponsible, arguing it distracted from the star's genuine scientific value. The debate revealed a deeper struggle: how to balance public curiosity with scientific rigor. Tabby's star became a case study in the pitfalls of clickbait science, where complex research gets flattened into sound bites, yet it also showed how a single cosmic oddity could reignite widespread passion for astronomy. Crowdfunding campaigns sprang up to support further observations, raising over $100,000 from amateur enthusiasts. The star's mystery even inspired a wave of new citizen science projects, inviting the public to analyze data alongside professionals. What lingered, though, was the star's symbolic power. Whether or not aliens were involved, Tabby's star reminded us that the universe is stranger than fiction, and that sometimes the most electrifying discoveries aren't answers, but questions. The media frenzy may have faded, but the star's legacy endures, a testament to humanity's unshakable urge to look up and wonder. While professional astronomers scrambled to secure telescope time and funding to study Tabby's star, an unsung army of amateur skywatchers and citizen scientists quietly took up the torch. These volunteers, armed with backyard telescopes, open-source software, and an unshakable curiosity, became the star's most dedicated sentinels. Platforms like the Planet Hunters project, where the anomaly was first discovered, evolved into global hubs for collective detective work, proving you don't need a PhD to contribute to groundbreaking science. Night after night, enthusiasts tracked the star's flickers, uploading observations to shared databases that professionals eagerly mined for clues. One of the most remarkable efforts sprang from crowdfunding. In 2016, when institutional telescopes were too oversubscribed to monitor Tabby's star continuously, astronomer Tabby turned to the public for help. Her Kickstarter campaign, Bring the Stars to the People, raised over $100,000 in just weeks, enough to secure dedicated time on the Los Cumbres Observatory network. Donors weren't just passive backers, they became co-investigators, voting on observing strategies and receiving real-time updates. When the star's next major dimming event hit in 2017, it wasn't a professional facility, but this grassroots network that caught it in action, providing critical data no automated system could have captured. The impact went beyond raw data. Citizen scientists brought fresh eyes to the mystery, spotting patterns algorithms missed. Some volunteers developed their own analysis tools, filtering noise from light curves with ingenious homemade code. Others cross-referenced historical star catalogs, uncovering subtle changes predecessors had overlooked. This distributed approach mirrored the star's own unpredictability, where a single observer in Japan or South Africa might be the one to catch a fleeting dip during their local night, while the rest of the world slept. Perhaps the most enduring legacy of this collaboration was how it reshaped public engagement with science. Tabby's star became a shared puzzle, transcending academia. Online forums buzzed with theories from teachers, engineers, and even high school students debating dust dynamics or orbital mechanics. The star's Enigma democratized astronomy, proving that breakthrough discoveries aren't just the domain of elite institutions. They can spring from a kitchen table with a laptop and Wi-Fi. And when professional papers were published, many included citizen scientist, co-authors, a nod to the collective effort. The star's story became a blueprint for how modern science could thrive, not in isolation, but as a conversation spanning continents and expertise levels. While the mystery of Tabby's star endures, one truth is crystal clear sometimes. The most powerful instrument in astronomy isn't a telescope, but the boundless curiosity of people willing to look up and wonder together. The summer of 2017 marked a turning point in the quest to unravel Tabby's star's secrets, because for the first time, astronomers were ready when the star began one of its dramatic dimming events. For months, telescopes around the world had been locked onto the star, poised to capture every flicker. Then, in May, it happened. Tabby's star's brightness plummeted by nearly 3% over just a few days. This wasn't just another dip, it was a golden opportunity. Las Cumbres Observatory's global network sprang into action, coordinating observations across multiple continents to ensure continuous coverage. Meanwhile, the Keck Observatory in Hawaii trained its high-resolution spectrograph on the star, dissecting its light across hundreds of wavelengths. For the first time, scientists weren't just watching the dimming, they were decoding it in real time. What they found reshaped the entire debate. The spectral data revealed a critical clue. The star's blue light dimmed more sharply than its red light during the event. This wavelength-dependent behavior was like a cosmic fingerprint, pointing squarely toward dust as the culprit. Solid objects like planets or hypothetical megastructures would block all colors evenly, creating a uniform dip across the spectrum. Dust, however, scatters shorter blue wavelengths more effectively, exactly as the observations showed. Even more telling, the dimming wasn't instantaneous, it began gradually, as if the dust cloud was diffuse, with its outer edges filtering starlight before its denser core passed fully into view. This ruled out rigid structures and pointed instead to something porous and uneven, like a celestial sieve. Yet the 2017 event also deepened the puzzle. While dust explained the wavelength dependence, the star's long-term fading and erratic dips still lacked a unified explanation. Some researchers proposed a two-tiered model, a vast, slow-moving reservoir of dust causing the century-long dimming, with smaller, dynamic clumps within it creating the sudden drops. Others wondered if the dust wasn't orbiting the star at all, but drifting through interstellar space, casting shadows as it passed between Tabby's star and Earth. The data allowed for both possibilities, leaving astronomers with more refined questions but no definitive answers. Then came another twist. In 2019, the star surprised everyone again with a series of rapid micro-dips, fluctuations so brief they lasted mere hours. These weren't the leisurely declines of previous events, but sharp, staccato flickers, like someone repeatedly tapping a cosmic dimmer switch. The Keck Observatory's spectrograph caught these micro-dips in action, revealing yet another layer of complexity. Some wavelengths dimmed faster than others, suggesting the obscuring material wasn't just dust but a mix of particle sizes, from fine powder to gravel-like grains. This chaos defied tidy classification. No single natural process could easily explain such frenetic behavior. Amid the confusion, one thing became clear: Tabby's star wasn't just an outlier, it was a laboratory. Every dimming event, every spectral line, added another piece to a puzzle that refused to snap into place. The dust hypothesis had narrowed the field, but the star kept throwing curveballs, as if taunting scientists with glimpses of an answer just beyond reach. And that's the essence of breakthrough science, not the eureka, a moment, but the relentless chase, the slow assembling of clues until the impossible starts to make sense. Tabby's star's greatest gift wasn't an explanation, it was the invitation to keep looking. If alien megastructures were obscuring Tabby's star, there's one glaring thing we should have detected by now: heat. Lots of it. Here's why: any object that blocks starlight, whether a planet, a dust cloud, or an alien solar panel, absorbs that energy and must re-radiate it. And in space, that energy doesn't just vanish, it gets emitted as infrared radiation, a telltale thermal fingerprint. Freeman Dyson himself predicted this back in the 1960s when he theorized about civilizations building vast energy-capturing structures around stars. The math was straightforward. If you're harvesting a star's light, you're converting it into usable energy, waste heat, or both. Either way, the laws of thermodynamics demand that heat must go somewhere. That's why astronomers immediately trained infrared telescopes on Tabby's star, searching for the unmistakable glow of warmed dust or metal. The results: nothing, no excess heat, no unexplained infrared signature, just the quiet background radiation you'd expect from an ordinary star. This absence punches a hole straight through the Dyson swarm hypothesis. Even the most advanced alien tech couldn't cheat physics. If megastructures were truly blocking 20% of the star's light, they should be radiating detectable infrared energy. The fact that we see no such signal suggests one of two things: either the dimming isn't caused by solid objects at all, or whatever's out there operates by rules we don't yet understand. But let's play devil's advocate. Could an alien civilization theoretically hide this heat signature? Some have proposed exotic workarounds. Maybe the structures channel energy into non-thermal forms, like directed beams for communication or propulsion. Perhaps they're radiating heat in directions we can't observe, or using hyper-efficient materials that dissipate energy at undetectable wavelengths. These ideas flirt with speculative physics, but here's the catch: they require technologies so advanced they might as well be magic. Science thrives on testable hypotheses, and right now, the lack of infrared evidence stacks the deck heavily against the megastructure theory. The infrared puzzle also casts doubt on simpler natural explanations. Dust clouds, for instance, should glow with residual warmth, yet Tabby's star's infrared readings remain stubbornly quiet. This paradox led researchers down a fascinating rabbit hole. Could the dust be unusually cold or far from the star? Recent studies suggest the particles might be microscopic and widely dispersed, acting like a cosmic mesh that scatters light without absorbing much heat. Or maybe the dust isn't orbiting the star at all but drifting in the interstellar medium, cold enough to evade infrared detection. These are plausible workarounds, but they demand precise, almost finicky conditions to align with observations. What makes this infrared silence so frustrating and thrilling is how it refuses to neatly resolve the mystery. Every time we think we've cornered an explanation, the data slips through our fingers. The absence of heat doesn't just challenge the alien hypothesis, it complicates all our models, forcing us to question whether we're even asking the right questions. Maybe Tabby's star isn't just teaching us about cosmic oddities. Maybe it's holding up a mirror to the limits of our own imagination. As the dust hypothesis gained traction, astronomers began exploring even more exotic possibilities, ones that didn't just think outside the box, but tore the box apart. What if Tabby's star wasn't just surrounded by random debris, but the apocalyptic wreckage of an entire shattered planet? Picture a world several times larger than Earth, torn to pieces by gravitational forces or a catastrophic collision, its fragments scattered into a sprawling, uneven disk. Unlike comets or dust clouds, the remnants of such a cataclysm could range in size from fine grains to mountain-sized boulders, creating a chaotic mix of shadows as they orbit. This wouldn't just explain the erratic dimming, it could also account for the star's long-term fading, as the debris slowly spirals inward or disperses over centuries. But here's the catch: destroying a planet isn't as simple as it sounds. For a world to fracture so completely, it would need to experience unimaginable violence, perhaps a head-on collision with another massive body, or a tidal shredding from venturing too close to its star. While such events are theoretically possible, they're astronomically rare, especially around a star like Tabby's, which shows no signs of the turbulent youth typically associated with planetary chaos. Even more puzzling, the aftermath of such a disaster should leave behind a detectable infrared glow as the rubble absorbs and re-radiates starlight. Yet Tabby's star's infrared signature remains suspiciously quiet, as if the debris is either impossibly cold or somehow evading the laws of thermodynamics. Another twist on this idea involves not one star, but two. Some researchers speculate Tabby's star might have an unseen companion, a smaller, dimmer star, or even a brown dwarf, circling it in a wide orbit. Around this secondary object, a colossal ring system, far grander than Saturn's, could stretch for millions of miles. As this hypothetical ringed companion moves along its orbit, its tilted rings would cast shifting, asymmetrical shadows across Tabby's star when viewed from Earth. This could explain the irregular dips, especially if the rings are patchy or warped, with gaps and clumps that filter light unpredictably. The appeal of this theory lies in its flexibility. Ring systems, unlike solid megastructures, can naturally exhibit complex, evolving structures. They're also known to exist. Just look at the young star J1407, which sports rings so vast they make Saturn's look like a child's toy. But Tabby's star's hypothetical rings would need to be on an entirely different scale, dwarfing anything we've observed. Even then, they'd face the same infrared problem as other theories. Rings absorb and re-emit starlight, so where's the heat? Unless the companion is so distant, its rings remain frigid, the math struggles to add up. Then there's the observational hurdle. If Tabby's star has a binary partner, why haven't we spotted it? Current telescopes should be capable of detecting even faint companions at the proposed orbital distances. Repeated searches have turned up empty, leaving the ringed companion idea lingering in the realm of maybe. But where's the proof? What unites these theories, the shattered planet, the phantom rings, is their sheer audacity. They're not just explanations, they're cosmic detective stories, each with its own tantalizing clues and frustrating dead ends. And that's the beauty of Tabby's star. It pushes us to consider scenarios we'd never dream of applying elsewhere. Whether any of these ideas hold up under scrutiny almost doesn't matter. What matters is that, in wrestling with this star's mysteries, we're learning to ask better questions, ones that might someday reveal not just the truth about Tabby's star, but secrets of the universe we haven't even thought to wonder about yet. One tantalizing possibility astronomers have explored is that KIC 8462852 isn't flying solo. It might have a hidden dance partner. Binary star systems, where two stars orbit a common center of gravity, are surprisingly common in our galaxy. In fact, over half of all Sun-like stars have companions. Could Tabby's star's erratic dimming be the work of a second, unseen star stirring up cosmic chaos? The idea isn't as far-fetched as it might seem. Binary systems can create environments where dust, debris, and even planets behave in strange ways. Imagine a scenario where Tabby's star's companion, perhaps a small red dwarf or even a faint white dwarf, looms just outside our current detection limits. As the two stars swing around each other, their gravitational tug-of-war could distort the orbits of planets or asteroids in the system, sending them careening into one another. The resulting debris field, stretched and sheared by the competing pulls of the two stars, might form a lopsided, ever-changing cloud that intermittently blocks our view. This could explain some of the star's most baffling traits: the irregular timing of the dimming events. That might be debris following chaotic orbits dictated by the binary pair's gravity. The long-term fading, perhaps a slow migration of dust toward one star or the other, gradually thickening the veil. Even the lack of excess infrared radiation could fit. If the companion star is cool enough, it might not heat the surrounding debris to detectable levels. But here's where the theory hits a snag. Despite exhaustive searches, astronomers haven't found any concrete evidence of a stellar partner. High-resolution imaging and careful analysis of the star's motion reveal no telltale wobble that would betray a companion's presence. Even if the hypothetical partner were a dim brown dwarf or a neutron star, its gravitational influence should still leave subtle fingerprints in Tabby's star's movement. So far, the data remains stubbornly silent. Some researchers have proposed a workaround. Maybe the companion is in an exceptionally wide orbit, taking centuries to complete a single loop around Tabby's star. In that case, its gravitational effects might be too subtle to detect within our limited observational window. Alternatively, the companion could be positioned in a way that currently masks its presence, like hiding behind the glare of the primary star. Future telescopes with even sharper eyes might eventually settle the debate, but for now, the binary hypothesis remains in limbo, compelling but unproven. Yet even without definitive proof, the possibility opens doors to creative thinking. Binary systems are cosmic petri dishes for unusual phenomena. Take the case of Epsilon Aurigae, another mysteriously dimming star that turned out to have a massive, disk-shrouded companion orbiting it every 27 years. Or VVVW8008, a giant star that dims by a staggering 80% at irregular intervals, likely due to a companion surrounded by a colossal, tilted ring of dust. Could Tabby's star be another example of these celestial odd couples, its secrets locked in an intricate gravitational ballet we're only beginning to glimpse? Whether or not a binary companion is the ultimate answer, the very pursuit of one reveals how Tabby's star keeps pushing astronomers to consider every angle. Sometimes, the most profound discoveries come not from finding what we expect, but from learning just how creative and unpredictable the universe can be when it hides its cards. The key to unlocking Tabby's star's secrets might not lie in the telescopes we have today, but in the ones we're about to unleash upon the cosmos. At the forefront of this next-generation arsenal is NASA's James Webb Space Telescope, a technological marvel designed to peer deeper into the infrared spectrum than any instrument before it. Unlike Hubble, which primarily observes visible and ultraviolet light, Webb's infrared eyes could be perfectly tuned to spot the heat signatures of the very dust particles thought to be obscuring the star. If Tabby's star's dimming truly comes from cold, diffuse dust clouds, Webb's sensitive instruments might finally detect their subtle glow, even if previous telescopes missed it. But here's where it gets thrilling. If Webb finds nothing, no dust, no heat, no natural explanation, the alien megastructure hypothesis, however improbable, could come roaring back from the grave. Webb isn't alone in this cosmic detective work. The Vera C. Rubin Observatory, set to begin its 10-year survey of the sky in the next few years, will monitor billions of stars with unprecedented precision. While it won't study Tabby's star continuously, its sheer observational power might catch dimming events other telescopes miss, building a richer timeline of the star's antics. Then there's the upcoming European Space Agency's Plato mission, designed specifically to hunt for exoplanets. By measuring starlight with exquisite accuracy, Plato could spot subtle patterns in Tabby's star's dips, revealing whether they're caused by orbiting debris or something even stranger. But perhaps the most tantalizing prospect lies in the realm of direct imaging. Future telescopes like the Habitable Worlds Observatory, still in the conceptual phase, aim to directly photograph exoplanets by blocking out their host star's glare. If trained on Tabby's star, such an instrument might capture the first real images of whatever's obscuring its light, whether a swirling debris field, a warped protoplanetary disk, or, in the wildest scenario, the geometric shadows of artificial structures. Even more exotic technologies are on the horizon. Projects like Breakthrough Starshot, which aims to send tiny probes to nearby stars, could inspire missions to study Tabby's star up close. Imagine a swarm of nanoprobes, each no larger than a smartphone, sailing toward the star on laser-driven light sails. While such a mission remains decades away, the mere possibility highlights how far we're willing to go to solve this puzzle. What makes these upcoming missions so exciting isn't just their technological prowess, it's their potential to transform Tabby's star from a mystery into a milestone. Whether they confirm a mundane explanation or unveil something truly revolutionary, one thing's certain: the star's final act has yet to be written, and when the next chapter unfolds, it might rewrite our understanding of the cosmos itself. Tabby's star didn't just baffle astronomers, it reshaped how they confront the unknown. Before its discovery, anomalies in stellar data were often dismissed as noise, glitches, or mundane outliers. But this star forced a paradigm shift, proving that even the strangest signals deserve scrutiny, not sidelining. It became a masterclass in balancing open-minded curiosity with disciplined skepticism, showing that the most profound discoveries often lie just beyond the edges of our expectations. Take the way scientists now approach citizen science data. Before Tabby's star, professional astronomers occasionally viewed crowdsourced findings with polite skepticism. But when volunteers from the Planet Hunters project spotted the star's bizarre dimming, something automated algorithms had missed. It validated the power of collective human intuition. Today, projects like Backyard Worlds and Zooniverse are integral to astronomy, harnessing thousands of eyes to spot cosmic oddities machines might overlook. The lesson: sometimes a fresh perspective, whether from a PhD or a cafe owner with a laptop, can crack open the universe's deepest riddles. Equally transformative was the star's challenge to scientific communication. The media frenzy around the alien megastructure hypothesis could have devolved into chaos, but instead, it sparked a vital conversation about how to discuss unproven ideas responsibly. Astronomers like Jason Wright and Tabitha Boyajian walked a tightrope, acknowledging the tantalizing possibility of extraterrestrial engineering while rigorously testing every alternative. This delicate dance, embracing bold hypotheses without succumbing to sensationalism, has since become a model for handling anomalies, from Oumuamua's interstellar origins to fast radio bursts. The public learned that science isn't about absolute answers, but the messy, exhilarating process of ruling out the impossible to reveal the merely improbable. Perhaps the star's greatest legacy is its reminder that nature loves to surprise us. For centuries, astronomy operated on the assumption that stars behaved in predictable, orderly ways. Tabby's star shattered that illusion, revealing the cosmos as a stage for the bizarre and unpredictable. Its erratic flickers forced astronomers to expand their playbook, considering everything from shattered planets to interstellar dust clouds, ideas that might have seemed outlandish a decade earlier. Now, when researchers encounter anomalies in data, they're quicker to ask, is this another Tabby's star? That shift from dismissal to disciplined wonder has already borne fruit. The discovery of other weird stars, like Epic 246747538 with its 6-day eclipses, owes a debt to the trail Tabby's star blazed. Underlying all this is a deeper philosophical lesson, the value of humility. For all our telescopes and supercomputers, the universe remains infinitely creative, capable of conjuring phenomena that defy our neat classifications. Tabby's star humbled astronomers by proving that even well-tested assumptions, like how planetary transits should look, can crumble when faced with reality's complexity. In an era where AI sifts through petabytes of data, the star stands as a testament to human curiosity's irreplaceable role. Algorithms excel at finding what we've programmed them to seek. But it takes a living, questioning mind to recognize the data point that shouldn't exist and to chase it into the unknown. So while Tabby's star may never give up all its secrets, its true gift wasn't an answer, but a revolution in how we explore. It taught us to wield Occam's razor lightly, to entertain wild ideas without abandoning rigor, and to remember that the next cosmic breakthrough might be hiding in plain sight, waiting for someone bold enough to say, "This doesn't make sense." Let's find out why. Tabby's star doesn't just challenge our understanding of stellar behavior, it throws a wrench into one of the most profound questions in science: where is everybody? This is the heart of the Fermi paradox, the glaring contradiction between the high probability of alien civilizations existing in our vast universe and the utter lack of evidence that they're out there. If the cosmos is so old and so spacious, why haven't we stumbled upon even a single unmistakable sign of other intelligent life? Tabby's star's eerie dimming patterns briefly seemed like a crack in that silence, a flicker of possibility that we might not be alone after all. Yet the deeper we looked, the more the star mirrored the paradox itself, teasing us with cosmic ambiguity, refusing to deliver answers. Consider the numbers. Our galaxy alone contains hundreds of billions of stars, many older than our Sun by billions of years. Even if only a tiny fraction host life, and a fraction of those nurture intelligent species, the math suggests the Milky Way should be buzzing with activity. Advanced civilizations, if they exist, would have had ample time to spread across the stars, building megastructures, sending signals, or leaving artifacts. And yet, our telescopes and radio antennas hear only silence. Tabby's star's fleeting brush with the alien hypothesis didn't just revive the debate, it sharpened it. For a moment, we dared to wonder, what if we've been looking for extraterrestrials the wrong way? Traditional SETI, the search for extraterrestrial intelligence, has long focused on hunting for radio signals or laser pulses, deliberate messages flung across the void. But what if advanced civilizations don't bother with whispers? What if, instead, they reshape their environments on scales so vast we'd spot the consequences before we'd ever hear a greeting? This is the premise behind Dysonian SETI, the hunt for cosmic engineering. Instead of listening for hello, we'd look for the shadow of a Dyson swarm, the heat signature of a stellar engine, or the unnatural flicker of a star under alien management. Tabby's star, with its bizarre light curves, became the test case for this audacious idea. Here was a star that just might bear the fingerprints of intelligence. But the paradox deepens. If societies advanced enough to build star-sized constructs exist, why haven't we found more of them? Why is Tabby's star seemingly alone in its strangeness? One harrowing answer is the Great Filter hypothesis, the idea that some catastrophic barrier prevents civilizations from reaching the interstellar stage. Maybe it's self-destruction through war or environmental collapse. Maybe it's an unavoidable technological bottleneck. Or worse, maybe the filter lies ahead of us, lurking in humanity's future. Tabby's star, if it had harbored aliens, could have offered hope that the filter isn't inevitable. Instead, its quiet fade back into ambiguity leaves us wrestling with darker possibilities. There's another, humbler takeaway. The universe might be stranger than we imagine, but not in the ways we expect. Tabby's star's eventual drift toward mundane explanations, dust, debris, stellar quirks reminds us that nature's creativity outstrips our sci-fi fantasies. The cosmos doesn't need aliens to produce jaw-dropping phenomena. It's already full of unimagined wonders waiting to append our assumptions. The Fermi paradox persists not because space is empty, but because it's so endlessly inventive in hiding its secrets. In the end, Tabby's star and the Fermi paradox share the same lesson. The universe resists tidy answers. Every time we think we've glimpsed a pattern, whether in the dimming of a distant sun or the silence of the sky, the cosmos throws a curveball. And that's the thrill of the hunt. The absence of aliens isn't a dead end. It's an invitation to look deeper, question harder, and stay open to the possibility that the truth might be wilder than we've dared to dream. Tabby's star didn't give us extraterrestrials, but it did something just as valuable. It kept the wonder alive. Tabby's star didn't just captivate scientists, it ignited a wildfire of creativity far beyond the halls of academia. Almost overnight, this unassuming flicker of light 1,500 light-years away became a canvas for humanity's wildest cosmic dreams. Sci-fi authors seized its mystery, weaving tales of ancient alien civilizations erecting monolithic structures to harvest stellar energy. Novels like The Citadel of the Starswarm cast it as the backdrop for interstellar empires, while indie game studios built entire narratives around decoding its secrets. The star's very name, once a dry catalog number, morphed into shorthand for the tantalizing unknown, a symbol of the universe's refusal to be easily understood. Hollywood took notice too. Screenwriters traded treatments featuring Tabby's star as the setting for first contact stories, its erratic dimming recast as alien Morse code or the wake of colossal spacecraft. One shelved Netflix pitch, leaked in industry forums, envisioned a team of astronauts arriving at the star only to find its megastructures abandoned. Their builders vanished into the void, a haunting metaphor for the Fermi paradox. While no blockbuster has yet centered on the star, its influence permeates speculative fiction, from throwaway dialogue in major sci-fi franchises to viral short films where its flickers trigger global existential crises. The art world responded just as fervently. digital renderings of hypothetical Dyson swarms, some sleek and geometric, others organic and tumorous, flooded online galleries like DeviantArt and ArtStation. At the 2019 Venice Biennale, an immersive installation recreated the star's light curves across a vaulted ceiling, inviting visitors to lie beneath its unpredictable glow. Musicians composed ambient soundscapes, translating its dimming patterns into eerie or rhythmic melodies, while poets penned verses comparing its inscrutable behavior to love letters from the cosmos, alternately revealing and obscuring their meaning. Even meme culture couldn't resist. Tabby's star became the face of cosmic absurdity, its pixelated silhouette photoshopped into conspiracy boards alongside Bigfoot and UFOs. Jokes about aliens forgetting to pay their starlight bill or the star being the universe's mood ring turned astrophysics into viral humor. But beneath the laughs lay something profound, a generation raised on clickbait and quick answers reveling in a mystery that refused to be solved. The star's cultural staying power stems from this very tension. It's a Rorschach test for the digital age, reflecting back our collective longing for wonder in an era of algorithmic predictability. Perhaps most unexpectedly, Tabby's star reshaped how we talk about science itself. Before its discovery, terms like Dyson sphere languished in obscure physics papers. Now they're part of mainstream discourse, name-dropped in TED Talks and late-night monologues alike. The star's journey, from fringe hypothesis to front-page news to cultural touchstone, blurred the lines between rigorous research and speculative storytelling, proving that the most impactful science isn't always about definitive answers. Sometimes it's about the questions that linger, sparking conversations around campfires and conference tables in equal measure. What makes Tabby's star truly unique isn't just its bizarre behavior, but how it holds up a mirror to human curiosity. In an age of instant gratification, it reminds us that some mysteries aren't meant to be solved quickly, if at all. It's become more than an astronomical anomaly. It's a shared story we're all writing together, one observation, one theory, one wild, artistic interpretation at a time. The star's greatest gift might be the permission it gives us to stand beneath the night sky and say, quite honestly, we don't know, and find joy in the not knowing. One of the biggest myths surrounding Tabby's star is that scientists seriously believe aliens built megastructures around it. While the idea made headlines and sparked imaginations, the reality is far more nuanced. Astronomers never claimed to have found extraterrestrial engineering, they simply acknowledged that the star's behavior was so unusual. They had to consider all possibilities, even the most speculative. The media, however, latched onto the alien angle, often glossing over the critical caveats researchers included in their papers. Headlines framed the megastructure hypothesis as a near certainty rather than what it truly was, a last resort explanation, only entertained after more plausible theories fell short. Another common misconception is that Tabby's star's dimming is completely unique. While its behavior is exceptionally bizarre, it's not entirely alone. Astronomers have since identified other Dipper stars with irregular light patterns, like Epic 24, 67, 47, 53, 8, which dims by up to 65% in cryptic 6-day cycles. The difference is scale and persistence. Tabby's star's fluctuations are both more extreme and longer-lasting, but it's part of a growing family of cosmic oddballs. This context often gets lost in sensational coverage, leaving the impression that this star exists in a class of its own. In truth, it's more like the most extreme member of a very strange club. Then there's the oversimplification of the dust explanation. Some summaries present it as the definitive answer, as if the mystery has been solved, but the dust hypothesis, while compelling, is still full of gaps. Yes, observations show wavelength-dependent dimming consistent with dust grains, but the lack of excess infrared radiation remains a thorny contradiction. Plus, the dust's origin and structure are still debated. Is it from disintegrating comets, planetary collisions, or something else entirely? Science rarely delivers neat, wrapped-up answers, and Tabby's star is a prime example of how messy discovery can be. Perhaps the most persistent myth is that the star's behavior defies all known physics. In reality, it challenges our expectations, not the laws of nature. Unusual doesn't mean impossible. Cosmic history is littered with phenomena once deemed inexplicable: pulsars, quasars, gamma-ray bursts that later found natural explanations. Tabby's star may well be another case of the universe revealing a process we simply hadn't encountered before. The real story isn't about breaking science, it's about science adapting to new puzzles. Lastly, there's the idea that Tabby's star's mystery is fading just because dust is the leading theory. Some portray this as a letdown, a retreat from the thrilling possibility of aliens. But that misses the point. Whether the culprit is dust, debris, or some undiscovered stellar quirk, the star has already transformed astronomy. It taught us to question assumptions, embrace collaborative discovery, and stay open to the universe's creativity. The real wonder isn't in proving aliens exist, it's in uncovering how much we still have to learn. Tabby's star didn't lose its magic by becoming less alien. It revealed something even more profound, that the cosmos thrives on surprises, and the next great discovery might be hiding in plain sight. Years after its discovery, KIC 8462852 continues to defy explanation, a cosmic riddle wrapped in starlight, daring us to unravel it. This isn't just another oddity in the vast catalogue of space mysteries. It's a full-blown enigma that has resisted every attempt to fit it neatly into our understanding of how stars behave. Most astronomical puzzles surrender their secrets with enough observation and analysis. Pulsars, once mistaken for alien signals, revealed themselves as spinning neutron stars. Quasars, initially baffling in their brilliance, were unmasked as active galactic nuclei. But Tabby's star, it plays by its own rules, refusing to conform to any textbook scenario or predictable pattern. What makes this star so uniquely frustrating and fascinating is how it dances just beyond the edge of comprehension. Every time a new theory gains traction, fresh data throws a wrench into the works. Take the dust hypothesis. While it explains the wavelength-dependent dimming, it doesn't account for the sheer scale and irregularity of the star's light drops. Or consider the long-term fading, a century-long decline that no known stellar process can comfortably explain. Even the most creative natural explanations, shattered planets, warped debris disks, rogue interstellar clouds, feel like forcing square pegs into round holes. There's always a lingering inconsistency that keeps the mystery alive. Part of the challenge lies in the star's sheer unpredictability. Most cosmic phenomena follow at least some rough guidelines. Variable stars pulse rhythmically. Exoplan, its transit on schedules you could set a watch to. But Tabby's star, its dimming events are as erratic as a flickering street lamp, with no discernible rhythm or reason. One year it might plunge into a dramatic fade, the next it could sit stubbornly quiet, as if taunting the astronomers trained on it. This capriciousness makes it maddeningly difficult to study. Unlike predictable celestial events, you can't just point a telescope at Tabby's star and wait for the next big dip. You have to watch incessantly, hoping to catch it in the act, always one step behind its next move. Yet the star's resistance to explanation is precisely what makes it invaluable to science. True breakthroughs rarely come from studying the ordinary. They emerge from investigating the outliers, the data points that don't fit. Tabby's star is astronomy's equivalent of a Rosetta Stone, not because it provides easy answers, but because it forces us to ask better questions. What if our models of stellar evolution are incomplete? Could there be entirely new categories of cosmic phenomena we've yet to imagine? The star's stubborn refusal to conform hints at gaps in our knowledge, territories of astrophysics still waiting to be mapped. And so the watch continues. Telescopes old and new keep vigil, from the Hubble's aging optics to the James Webb Space Telescope's infrared eyes. Citizen scientists sift through data, searching for patterns machines might miss. Astronomers debate, publish, and debate some more, weaving an ever-expanding tapestry of theories. Tabby's star has become more than an object of study. It's a collective challenge, a reminder that the universe is under no obligation to make sense to us. Whether the final answer turns out to be mundane or mind-blowing, one thing's certain: this star has already changed how we explore the cosmos. It's taught us humility, curiosity, and above all, the thrill of chasing something just beyond our grasp. In a universe that often feels increasingly mapped and measured, KIC 8462852 stands as a beacon of the unknown, whispering that there are still wonders left to uncover. The enigma of Tabby's star has done something remarkable for the search for extraterrestrial intelligence. It's forced scientists to broaden their definition of what alien technology might look like. For decades, SETI focused narrowly on hunting for radio signals or laser pulses, the cosmic equivalent of a deliberate hello. But this star's strange flickers introduced a radical alternative. Maybe advanced civilizations don't bother with messages. Maybe they leave behind something far more visible, the fingerprints of planet-scale engineering. The mere possibility sent shockwaves through the field, inspiring a new wave of Dysonian SETI that scans the cosmos not for whispers, but for shadows. Projects like Glimpsing Heat from Alien Technologies or G-HAT now scour telescope data for unnatural infrared signatures, while others analyze starlight for the telltale asymmetry of artificial structures. Tabby's star became the test case for this paradigm shift, proving that even if the answer turns out to be dust, the question was worth asking. What makes this star so pivotal is how it bridges the gap between science fiction and rigorous science. Before its discovery, the idea of searching for megastructures was often dismissed as fringe speculation, but here was a real, observable anomaly that matched, at least superficially, the theoretical predictions of Dyson swarms. Suddenly, papers on interstellar engineering weren't just thought experiments. They were frameworks for analyzing hard data. Researchers like Jason Wright began developing quantitative metrics to distinguish natural dimming from potential technosignatures, turning what was once speculation into a legitimate branch of astroengineering. The star's refusal to fit neatly into any known category became a catalyst, pushing SETI to mature beyond its radio-centric roots and embrace a more expansive, multidisciplinary approach. Yet the star's greatest lesson might be one of humility. While it reinvigorated the search for alien civilizations, it also underscored how perilously close we are to seeing patterns where none exist. The human brain is wired for agency detection, interpreting random events as deliberate actions. In ancient times, this instinct attributed thunderstorms to angry gods. Today, it might lead us to mistake cosmic dust for alien megastructures. Tabby's star served as a cautionary tale, reminding scientists to temper excitement with skepticism, to let data not desire drive conclusions. That balance is now baked into modern SETI protocols, where potential technosignatures must pass increasingly stringent tests before earning serious consideration. The ripple effects extend beyond academia. Public interest in SETI, which had waned after decades of silent skies, surged anew thanks to Tabby's star. Crowdfunding campaigns for technosignature research gained traction, while mainstream media began covering the field with renewed respect. Even NASA, traditionally cautious about associating with alien hunts, allocated funding to study anomalous stellar signatures. The star's cultural resonance gave SETI a second wind, proving that the public craves not just answers, but big, audacious questions. Perhaps most importantly, the star expanded our imagination of what's possible. If a civilization could build structures vast enough to dim a sun, what else might they achieve? Could they manipulate black holes for energy, rearrange star systems into computational arrays? Tabby's star didn't just revive SETI, it gave us permission to dream at galactic scales, to consider that the boundaries of technology might extend far beyond our current understanding. And that, in the end, is its enduring gift, not proof of aliens, but the thrilling uncertainty that keeps us looking up. From unexplained dimming patterns to tantalizing theories of alien megastructures, KIC 8462852, Tabby's star remains one of space's most captivating puzzles. This unassuming flicker of light, 1,500 light-years away, has rewritten the rules of stellar behavior, challenging our deepest assumptions about how stars and planetary systems evolve. We've chased answers through comet swarms and dust clouds, through shattered planets and phantom companions, only to find each explanation falling just short of the mark. The star's erratic flickers and century-long fade resist categorization, reminding us that for all our technological prowess, the cosmos still holds mysteries beyond our current understanding. What makes Tabby's star so extraordinary isn't just its strangeness, it's how it has transformed the way we explore the universe. This single anomaly taught astronomers to value outliers, to listen to citizen scientists, and to embrace bold questions even when they defy convention. It blurred the lines between rigorous science and imaginative speculation, proving that the most profound discoveries often begin with a simple admission: we don't know. Whether the final answer turns out to be mundane dust or something far more revolutionary, the star's legacy is secure, a beacon of curiosity that redefined how we hunt for cosmic anomalies. And that raises one last, thrilling possibility. If a star as seemingly ordinary as this one can harbor such profound secrets, what else might be hiding in plain sight? Our galaxy alone contains billions of stars, each potentially hosting its own unsolved riddle. Could another KIC 8462852 be lurking in Kepler's old data, waiting for a sharp-eyed volunteer to spot it? Might future telescopes uncover phenomena that make Tabby's star look tame by comparison? The universe has shown us time and again that its creativity dwarfs our imagination. So as we keep watching this enigmatic star, let's also train our eyes and our minds on the countless cosmic puzzles still waiting to be unraveled. After all, the next great mystery might already be whispering to us across the light years. Are we ready?